Hi, I'm Jamie with Chegg Tutors. Today I want to talk to you about Avogadro's law, something formulated in the early 1800s that took a long time to be accepted, but is now very useful for chemistry problems. Very simply, Avogadro's law might seem intuitive. It says if you have two gases, say it's hydrogen and oxygen, H2 and O2, and they're at the same temperature and pressure, and they have the same volume, there's going to be the same number of particles. Now, we know that the number of particles can be thought of as the number of molecules. When Avogadro formulated this, he had no idea about this. So a lot of the problems that we do are not going to use something you might recognize from earlier chemistry, like Avogadro's number, converting between number of particles and, say, 1 mole of a substance. So we're just going to use this to convert between number of particles or volumes and relative masses, weights, or volumes, mostly. Let's think a little bit about the history. So Avogadro proposes this law in the early 1800s. He's a lawyer in Italy, and he's competing with people like Berzelius, Dalton, and Guy Lussac, people in Germany, England, and France. Of course, the Napoleonic Wars are going on, just a little history for you, and these guys are not communicating with each other. Every person from a different nation is very secretive and proprietary about their knowledge. And Avogadro himself, he's a lawyer. He's not in the main current of scientific research in any of these countries. He's in Italy. And he barely has any scientific status at all. He's very isolated, and in fact, his work kind of invalidated a lot of the experimental work that other people, especially giants like Dalton, had done on the weight of certain molecules. So he is very much discredited. It takes a long time for this law to come into practice. At the time, also, they had no standard way to measure the molecular weight of something. They didn't even have a good idea of what a molecule or an atom was. They didn't know that hydrogen or oxygen gas is diatomic, and they had no idea how many particles are in a certain volume, say, of a gas. So Avogadro doesn't say how many particles there are. He simply says the number of particles for equal volume, temperature, and pressure is the same. Later on, when we have the concept of a mole, much later on, we're going to find out that at standard temperature and pressure, 25 degrees Celsius and 1 atmosphere, you have 22.4 liters of a gas is equal to 1 mole of particles. There's 1 mole of gas molecules in every 22.4 liters, no matter if it's water vapor, oxygen, or something that's a lot heavier. We can use this to solve quantitative problems now. We can use this to find a number of particles because we have Avogadro's number. We can also use this simply to relate the volume of two quantities of gas. So you might have, say, 5 liters of hydrogen. You have 5 liters up here. And you might say you have 2 moles. Now this is not at standard temperature and pressure, because we know that at standard temperature and pressure, 22.4 liters per mole. This is clearly not that. But we can use it if we know how many, what the new volume is. Say it's 10 liters. It's a very simple problem. We know that this N2 is going to be twice the number of moles, 4 moles. So this lets us convert between volume and number of particles represented this time in moles, which are a lot easier to work with than individual molecules. At the time, Avogadro's number really helps scientists, and scientists now as well, to determine the molecular weight of something by measuring the mass of a gas. Measuring the mass of a gas is something they can do even in the early 1800s, so they can use this to gain more experimental data on how much individual molecules weigh, without even knowing really what a particle of a certain substance really looks like. it's a connection between the micro world of atoms and molecules and the macro world of volumes and masses that we can actually measure. Now, I just want to make it clear that there are some assumptions. This only holds true for ideal gases. So gases where the particles are so small that there aren't really interactions between the particles, like intermolecular forces, van der Waals forces, or dipole-dipole forces in a polar molecule. We assume that the size is so small also that that the volume of the gas, in terms of the volume of the space that's around it, is basically zero. The particles are small enough that the particles themselves don't take up any space. It's simply the collisions between the particles and how much space the gas takes up as a whole. The other assumptions that we're making for ideal gases. I just want to make the point that the measurements for molecular weight that are calculated using Avogadro's law might be a little tiny bit off because these are real gases we're dealing with and not ideal gases. That's it for now. If you have more questions, take a look at the other videos or check out the actual tutor profiles on Chegg. Thanks for watching and see you next time.